Hello, this is the demo for probability for deep learning notebook. So, yeah, in this we will see how the probability theory is applied in deep learning. So, probability theory is a mathematical foundation of all deep learning, from neural network training neural networks to understanding model uncertainty. Probability is everywhere. So let's see why it matters. Yeah, so there's this probability distribution which we learned in the previous notebook, that is really helpful in weight initialization and output predictions. Bayes theorem is the Bayesian. It is useful in the Bayesian neural networks and its uncertainty estimations. Expected value is for loss functions and risk minimization. Entropy for cross entropy loss, which is used for classification and information bottleneck. KL divergence for variational autoencoders and knowledge distillation and regularization. Maximum likelihood is training objective for most neural networks. Sampling for dropout, dedocumentation and generative models. So in this we will learn the probability fundamentals like events, axioms, rules, conditional probability in the Bayes theorem, random variable, probability distribution, other key distribution, etc. So let's move to the first part. It's probability fundamentals, which is what is probability, which we have already cut. I'll skip for now. How the sample size, what the sample size is, and event. Yeah, just to recap, sample size is all possible outcomes and events are the subset of sample space with basically the outcomes that we care about. So yes, so for rolling a dice, the sample space is 1, 2, 3, 4, 5. So these are the all possible outcomes, and the event will be, let's say red is even numbers, so probability of getting even numbers is 2, 4, 6, and odd number is 1, 2, 1, 3, 5. So that is event. Now its connection with the deep learning, because in neural networks we want the probability, the output in a probability distribution format for each class. So let's say we have a cat, dog, bird, fish and rabbit as our output, possible outputs. But what is the probability that it's a cat, it's a dog, bird, fish and rabbit, and then whichever is the maximum, that then we say that it is, this is the probable answer for it. So that is there. So there this Kolmogorov axioms, also known as probability axioms. So these are the three basic theorems on which the probability is built. So first is non-negativity. So probability will always be negative for an event. If it is not going to happen, it's just zero, but it can never have a negative value. Normalization is the probability of the whole sample space must be equals to zero. That we have seen that all the probabilities, all the sum of these probabilities should equals to zero, because that even has to happen. So that is certain. Then additivity, for mutually exclusive events we can add the probabilities again. If they are not mutually exclusive, then we have to minus a and b, probability of happening a and b together. So that is there. We did that actually in the previous notebook. So again, yes, so this is event A and this is event B. Event A is finding the even number, and event B is any number greater than 5. So here in this, there's in this Venn diagram, the 6 occurs in both. So in this case the probability, probability of A is 0.5, probability of B is 0.33, and the probability of A and B is 1/6. because the probability of A and B is basically happening both together is this 1 by 6. 6 is the sample space, so that's why 0.1517. The probability of A or B is probability of A, probability of B minus probability of A and B, and that will give us this value. Now conditional probability. The conditional probability is the probability of an event given that another event has occurred. So the probability of A given B has happened is probability of A and B divided by B. Now this is the conditional probability. Based on that, we have Bayes' theorem. Bayes' theorem is A of A and B. A probability of A given B has happened is probability of B given A has happened dot A. So this is taken as likelihood. What is the likelihood of that happening? And this is the prior. What was the even without B has occurred, what is the probability of A happening? And probability of B is taken as evident, and that gives us posterior probability. So yeah, if your test is positive, do you have the disease? So when this is our question, so let's apply Bayes' theorem to it. So possibility of disease given your test came positive will be you how probability of testing positive given you have the disease, which is the likelihood, into probability of having the disease individually, which is the prior, divided by probability of getting a positive result, which is our evidence. When we do that, we get this possibility. So this means only 8.8% chance of disease despite positive test. So why so low? Because the disease is rare, so most positives are can be positive, false positives as well. Yeah, that is just the visuals of the same which I just explained. Then we have this expected value, variance, and moment. Expected value is mostly mean, average of your outcome. So for discrete values, it will be sum of x multiplied by probability of x happening. Or for continuous, it is limit negative to positive x multiplied by function of x dx. Again, now we have variance. Variance measures how spread out values are from the mean, and standard deviation is the square root of the variance. So let me just, yes, so this light green has, so for all these the mean value is 0, but for this light green has a huge variance because the values are varied. They are not very, they are varied across the spectrum. They are not specific to that. In contrast, if you look at this dark blue, this has less variance because they are converging around -2 to 2 values. Here you can see the variance for light blue is 0.5, whereas the variance for the light green is 4 because it's huge. So that is there. So we want to always reduce our variance, because then in this the probability, the sample space increases, which and we want to keep it less because we want to increase our possibilities of happening, like we want to increase our chances of having that event. So yeah, that should be our goal throughout. uh, then we have the loss functions. Excuse me. Yeah, there are then different types of distribution, as we spoke in the previous notebook. So here Bernoulli's is for discrete, and it's a discrete type of distribution where used majorly for binary classification, like 0 to 1. It will give you the values between 0 to 1. Categorical is for multi-class uh, classifications, and it's also discrete. Then we have Gaussian, which is a normal curve, which is used for continuous values, and it is used for weight initialization. So it basically that follows normal distribution, so it averages around some value, like we saw here in this graph. So we have the range from -6 to 6, but the majority of the values fall in this curve. So that is normal distribution. Then we have uniform, which is continuous, and it is also again used for weight initialization. So this is also so this is every value has almost equal possibilities, doesn't averages around a particular value. So yeah, that is normal uniform distribution. I think it is explaining the Bernoulli's. So yeah, Bernoulli's distribution is probability of as I mentioned, it works well with the binary classification. So probability of failure and probability of success. So it's a binary Bernoulli's distribution, whereas this is the Gaussian or normal distribution, where values, even though the sample space is from -4 to 4, but the most of the values are averages around particular value. So in this case it's 0, -1 to 1, and the mean is this. So again, this is 66% is 1 sigma, this is 2 sigma, 3 sigma. So we actually want our values to be always within normalization, because as I earlier mentioned, we wanted to keep it increase our possibilities rather than giving all the random values. We wanted to have a particular increase the possibilities, so that's why we normalize. Then entropy measures the uncertainty or surprise in the probability distribution. So this is the formula for that. So high entropy means high uncertainty, and low entropy is low uncertainty. So we want, yeah, so in uniform distribution, so all the values have equal possibility of happening. So then it is very, yeah, it's very difficult to find out which will occur, because each value has same possibilities of happening. So predicting that is quite difficult. But when we have low like peaked distribution like this, then finding out what is the possibility of happening this is really it is possible. So yeah, this is the diagram I was telling about. Uniform distribution is every class has equal possibility of happening, but whereas peaked is one class has more possibility than the others. So it's easy to guess or choose. So yeah, Then we have cross entropy. Cross entropy measures the difference between the two possibility distributions. This is mostly used for classification. This law as a loss function. Yeah, this is the most common loss function for classification. Um, hmm. So this is the perfect score where this was the true class and it predicted this as the one, not the others. But let's say in some other case it shows it did classify C2, but 0.8%, sorry, point with 80% possibilities, and given other possibilities to other classes as well. So in this case the loss is 0.22. So in the classification we want to decrease our cross entropy loss, and so yeah. Then we have this KL divergence, which is Kullback-Leibler divergence, which measures how one distribution differs from other, and this is used in variational encoders and knowledge distillation. Let me. So this is the data. So for a zero, the density is this like that. But yeah. So then we fit our model, and the model fits and it finds this curve, bell curve, and the variance at x, which is 4.79 in this case. So now it follows a bell curve. Now, yeah, so we this is the negative log likelihood for the classification. So then sampling is essential for training and inference and deep learning. So mini batch SGD is such sample batches from training data. Dropout is sample which neurons to drop out, and variation encoder and GANs are for samples for latent distributions. Monte Carlo estimation is approximate expectations. So deep learning connection is Bayesian theorem again. In Bayesian deep learning, we treat weights as probability distributions. So PFW is the prior belief about weights, and this is likelihood of the data given weight, and posterior is belief after seeing the data. So this is we want to find out, and these are the earlier possibilities which we know, which is what the Bayesian theorem is about. So then we have random variables, again discrete and continuous, and it follows this is Bernoulli's that has values from 0 to 1. This is following a standard normal curve, which is mostly used for regression problems. Yeah, probability mass function and probability density function. Its density is used for continuous variables. Probability mass function is used for discrete discrete values. Okay, this is the PMF for discrete values, how it looks, and this is the PDF of the continuous values. So here you can see for each class the values coming like this, and here it averages around a mean. Now, Monte Carlo estimation. Monte Carlo methods use random sampling to estimate quantities that are hard to compute analytically. So, this is the formula for that, and yeah, this estimate converges to the true expectation, so which is the law of large numbers. Um, so, yeah, uh, yeah, it's so basically Monte Carlos is you do then an experiment, and initially it will have some variance, but as you increase the sample size, it will converge to a particular to the predicted value, to the true probability. So increasing the number, so central limiting theory basically, it more samples means better estimate and there will be lower variance, so and which is the case in deep learning. Yeah, here is the distribution, error distribution. So with only 10 samples the variance was really high, but as soon as we increase the samples size, the variance decreases, and which is what we want in our in our model, in our neural network model, because we want precision. And the mini batch sampling in ST, stochastic gradient descent, this is the formula for that. Again, the gradient, larger batch size equals to lower variance but slower per epoch training, but the sweet spot is batch between 35 to this thing, because we also don't want, because the compute is also really high, so we cannot always do that, always use that, but so it's very important to find the sweet spot which balances speed and gradient quality. So you can use that, do that using the plot by plotting like this. Then we have this. Then yeah, in this one we are this is implementing the softmax from scratch. Yeah, so softmax is also it's used for multi-class multi-classification. Yeah, so that is pretty much it. Thank you.